Okay, so now I need to implement backpropagation. So I will implement 3 methods for my module. The forward that we have done for the dense module. Then I will implement the backward. The backward method will take a gradient of the loss with respect to the output and will convert it as the loss, as the gradient of the loss with respect to the input. And the update will take the gradient of the loss with respect to the output and compute with this quantity the gradient of the loss with respect to the parameters. So okay, we will do it for our loss function. Here, I will use binary cross entropy. So it's a loss function that will take one prediction and the true label. Let's say we have, it's a binary classification problem. So if y is equal to 0, this term will disappear. I will have minus 1 minus 0, so I will have minus log of 1 minus my prediction. This prediction can have values between 0 and 1. It's the probability of the image 2. And because this probability is the probability is associated to the presence of 2, if y is 0, it means that the true label is that there is no 2. So the probability of not having a 2 in the image is 1 minus p. It's 1 minus my prediction. So this term is activated when y equals 0. If y equal 1 here, the true label is 1. This term disappears, 1 minus 1 equals 0. And this one will be activated. And now I just have minus log of the probability of 2. And if the probability is 1, log of 1 is equal to 0, which means that I have no loss. So this binary cross entropy, I recommend you to look at it more carefully later, but it implements in some way if my model is predicting well or not the right label. And it's differentiable. So if it's differentiable, I can take the derivative of this function with respect to y hat, and this is the expression. As an exercise, you can also do this tonight. And now that I have this information, I can code it in my backward method. There's no parameters associated to this model. So it will just take a value here and compute the gradient of the loss. It will take the 2 values here and compute the gradient of the loss with respect to this quantity, with respect to the input. And this is what we want to implement in the backward. Okay, the next one is the sigmoid here. Sigmoid, the forward will be this expression that we have seen. The derivative of the sigmoid will be expressed as sigmoid, so I can program it in the backward method. And sigmoid doesn't have any parameters, so nothing to code for update. Now I have my dense module. Dense, I will receive a vector H. I will do my matrix vector multiplication plus b. So the backward, we see that it was only, the derivative will be w. And the update, I must implement it because I have parameters inside this module. And it will be H transpose and identity for b. And remember in my first example of the computational graph, to evaluate the derivative, I must know what are the intermediate values of the y nodes. So I must do a forward to know where am I in this space. So I evaluate all the variables. And when I know the values of these variables, I can compute the derivative at this specific place in the space. So I will do one forward over my model, and then I will do one backward in the opposite direction. So the chain rule will be this expression. A way to verify that this expression made sense, here it's like I want to compute the derivative of the loss with respect to the input. We'll see that it can be useful in certain application, but it's only for this exercise. And the chain rule, the way to verify it is if you consider these symbols as fractions, you can cancel out the numerator and the denominator of this expression. And so you will just, at the end, have dl over dh0 if you cancel out. It's not, I hope that no mathematician will talk to me about, at the end of this talk to tell me that I shouldn't have said it. It's not really something that we can do, but it's only a trick to remember the chain rule. So we want to compute all the elements of this expression. And the first one will be derivative of the loss with respect to the prediction of my model. And it will be a scalar here. Then I arrive at this module. I call the backward method derivative of the prediction with respect to this representation H3. And I have another scalar. And then I multiply the two together to obtain one single scalar. And then I can combine it. So now I have this quantity, derivative of the loss with respect to H3. I will give it to the backward method of my dense module. And in the dense module, I also need to do the update. So I will compute the derivative of the loss with respect to H3 that I receive as an input of my update method. But here I will compute the derivative of H3 with respect to all parameters of my linear transformation. And so I can multiply the two. I can do the same thing for derivative of H3 with respect to the bias, and I multiply the two. So now I have the derivative of the loss function with respect to these parameters, but I want also to have the derivative of the loss function with respect to these parameters, so I must continue to go back in the computational graph. So now the backward method for the dense modules, I will compute the derivative of H3 with respect to any of the component of H2. It's a gradient here. I can merge the two by multiplying these two quantities. I obtain the derivative of the loss with respect to H2. Now I have my activation function. What is interesting with the activation function is that it's transformed the representation component by component. There is no link between the component. So if I change the value of this representation, only this representation will change. I will not impact other representation, other components of the representation. So this matrix is called the Jacobian. I don't remember the convention, but let's say that rows are input and columns are output. So this matrix contains all the partial derivative of if I change this component, how the output will change. But here, since it's a component-wise activation function, the structure is diagonal. And I can multiply the two again. And now I have the derivative of the loss with respect to H1. And I'm doing the same for the loss for this module. And I can even take the derivative of the loss with respect to the input, to the image. And we will see what we can do with this information. So as you have seen in these slides, I use vectors and matrices to represent the chain rule. And so it's also linear algebra. So the forward with the dense modules and the activation function, it's mostly linear algebra. I can use GPU to implement it very efficiently. Since I'm computing a linear approximation of any change of the parameters, how the output will change, the linear approximation, by using the chain rule, I can also use matrix-matrix multiplication and linear algebra. And what I'm really doing is to multiply Jacobians. So the Jacobians will be only a quantity that will say if I change the input, how any output will change. And I will do Jacobian times gradient multiplication, matrix times vector multiplication. I still have 1 degree of freedom here to do matrix-matrix multiplication. So here I will stack multiple examples instead of doing only one example at a time. And so I will do matrix-matrix multiplication. Okay, so I did it in my life. I implemented these 3 methods. That's why I was doing it on the slides. We don't need to do it anymore. We just have to specify the forward method, and by a very sophisticated technique in automated differentiation, PyTorch and TensorFlow will create the backward and the update function for you. It will look at the mathematical operation that you will use. It will decompose it and code for you the derivative of this function. And it was also for those like dense or very popular activation function. They have also been implemented very efficiently at the GPU level. So there's a lot of things that have been implemented. If you want to create your new module, a new idea, you just have to specify the forward, and then the backward and the update will be created for you. Before, it was very painful. It was like, we have this new idea. We do a lot of computation on the paper to derive our expression, and then we code it. There are some bugs. It takes 2-3 weeks to find the bug that it was a plus instead of a minus. And since automated differentiation, the speed of the research is much, much, much faster.